Hello and welcome to the topic Introduction to the Atom. In today's lesson we're going to learn what is an atom. Now while we're discussing this topic, Introduction to the Atom, I want you all to remember the big idea, and that is, what are atoms and what are they made of? So specifically in this lesson we're going to learn about what is an atom, how would you describe the size of an atom, and how has the atomic model changed over time. So let's look at some key vocabulary. The first word being, obviously, atom. Atom is the smallest piece of an element that still represents that element. An electron is a particle with one negative charge within the atom. You also have the nucleus, and that's most of the atom's mass, and its positive charge is concentrated in this little small area right in the center. Now in that nucleus you will find protons, which is the atomic particle that has a positive charge, and neutrons, which is inside the atom and it has no charge, it's neutral. Now the electron cloud is this area around the atomic nucleus, and that's where all the electrons will be. They float in like a cloud around the nucleus. So let's go ahead and begin your lesson. Now let's look back about 2,000 years ago, all right? And a guy named Democritus, he basically came up with this thing and he called him atomos. And he had this atomic theory. He said that atoms are small solid objects that cannot be divided, created, or destroyed. He also said atoms are constantly moving in empty space. And different types of matter are made of different types of atoms. And the properties of atoms determine the properties of the matter. So here's this guy 2,000 years ago, and he was pretty spot on. He was very close. But what happened was, everybody knows Aristotle. Aristotle was much more influential. Everybody knew him. And he said, no, there is no empty space. Instead, all matter is made up of the four elements: fire, water, air, and earth. And because everybody knew Aristotle, and because he was so important, everybody took Democritus's ideas and pushed them aside and said, no, we're going to listen to Aristotle. And so nobody really looked at Democritus's ideas for another 2,000 years. And then along came John Dalton, who was a scientist, and he started doing some research, and he proposed a new atomic theory. Now, you'll notice it's some similarity to what was already discussed 2,000 years ago. But he said, all matter is made of atoms that cannot be divided, created, or destroyed. All right? He also said during a chemical reaction, atoms of one element cannot be converted into atoms of another element. He also said atoms of one element are identical to each other, but different from atoms of another element. And he said that atoms will combine in specific ratios. So that was his atomic theory. Now, this was the Greeks who said atoms determine properties, right? Water, iron, etc. Dalton said atoms determine the composition. So you can have different atoms put together. So atoms of different elements are different sizes. But, regardless, all atoms are small, right? We can't see them with our eye. We have to use a microscope. So you have a hydrogen atom right here as one proton. You have a hydrogen atom, again, one proton, and carbon atoms, 6 protons. So this is kind of a representation. Now, how would you describe the size of an atom? Well, as we said, they are very, very, very small. So if you expand the hydrogen atom to, let's say the size of an apple, then you would have to keep it the ratio is the same. You would have to take a real apple and expand it to the size of the Earth. That's how small atoms are. And again, we cannot see atoms with our eyes. Now, in 1981, they started coming up with these high-powered microscopes. So they're called scanning tunneling microscopes, or STMs. And this allowed scientists to actually be able to see individual atoms for the first time. So this is how long it took us. They're so small, we couldn't begin to see individual atoms till 1981. But then what happened, once they were able to see them, they learned that they are not the smallest particles of matter. So atoms are actually made up of other matter. And what you had is this scientist, J.J. Thompson, all right? And he did an experiment with cathode ray tubes. And he had small negatively charged particles, which he called electrons, that he found by doing this experiment with this cathode ray tube. So J.J. Thompson said, there are electrons in an atom. And it is, electrons are negatively charged. Now, because atoms are neutral or not electrically charged, Thompson proposed that atoms also must contain a positive charge that balances the negative charge. So he found these negative elements inside an atom. He said, well, wait a minute. Atoms are neutral or they're positively charged. So there must be something else in there that is positively charged that's balancing these out. And he proposed that the atom was a sphere, right? And, you know, like a ball with a positively charged, with a positive charge spread throughout and a negative charge within. All right, so that was his idea of what this looked like. Must have both positively charged sphere and then inside it negatively charged electrons. So he made a model of the atom with all this positive sphere and the negative charges within, and he called it his plum pudding atom, right? And kind of showed what it would look like. So you have these electrons and then all this positively charged, pudding, this material, positively charged material that it's all the electrons are floating in. Then Ernest Rutherford came along and he started doing some experiments and he learned more about what the atom contained. So what happened is he expected the positively charged particles, alpha particles, to travel straight through his gold foil without changing direction, right? So he shot this alpha particle source, and he expected it to go straight through the gold foil and hit the back. But what he found is that some, when he shot it through, some changed direction, some bounced back, and some went through in different directions. So it went all over the place. It just scattered. So it didn't happen the way his hypothesis said it would. Now, given the results of the gold foil experiment, how do you think an actual atom differs from Thompson's model? Remember, Thompson's is that plum pudding. Plum pudding with the electric and positively charged pudding that the electrons sit in. Well, we realize that Rutherford's model showed that there was something in the middle of the atom that was causing the particles to change direction or bounce back. Now, remember, Thompson said it was just a sphere with the positive charge evenly spread throughout and a negatively charged electrons within. So there was something in that atom, according to Rutherford, that was blocking the alpha beam or making it divert. So what was that inside that atom? So Rutherford concluded that most of the atom's mass and positive charge were centered right in the middle of an atom, in the nucleus. So this is Rutherford's atomic model. He started saying, well, wait a minute, there is a most of the atom's mass is, and it's positively charged, and it's right in the center of the atom, and it's called a nucleus, and it sits right there. So he kind of updated the model from Thompson's plum pudding model. Now, it also, after doing more research, they said, okay, well, these positively charged particles are in this nucleus, and we're going to call them protons. So a proton is a positively charged atomic particle, right? So you have now the nucleus, which he said exists, and you have the electrons, which are negative, and they're spaced around the nucleus, right? So now you've got the different parts of an atom coming together. Now, Rutherford's contains a very small, dense, positive nucleus. And these tiny electrons travel in empty space around the nucleus, right? So that was his model. The positive nucleus with all the protons and the negative electrons spinning around it. Then comes a guy named James Chadwick. And he said, well, wait a minute. In the nucleus, there's not just positive protons. There's also neutrons. Neutrons are neutral particles. So you went from Thompson's plum pudding, then you went to Rutherford, saying, oh, well, there's a positive nucleus. And now James Chadwick comes along. He says, well, wait a minute. Yeah, there's a nucleus, but there's also some negative particles inside there. So then he updated the model again. And then a guy named Niels Bohr said, well, the electrons move in a circular motion around the nucleus. And the nucleus is made up again of those neutrons and protons we just talked about. He said that any electron that's closer has less energy than the electrons farther away. So that was his idea of taking all the information that all these other guys had come up with and making his own model. Now, although electrons have specific amounts of energy, they found, after more research, they're not in circular orbits, right? And when an electron moves from high energy level to low energy level, the energy is released, sometimes as light. But they said, no, this doesn't have, electrons aren't like the Earth circling the sun. So in Bohr's model of the atom, electrons moved in circular orbits, right? So when energy is added to a hydrogen atom, the electron moves from the low energy to other higher energy levels. All right, so it moved from the first to the fourth level. And when it moves from the fourth to, let's say, the third level, energy is also released. So that is what Bohr's was saying, that all these electrons move in a circle and they release energy and move up and down in their circular path. So how did Bohr's model of the atom differ from Rutherford's model of the atom? Well, in Bohr's model, electrons moved in circular orbits. And in Rutherford's model, negatively charged electrons travel in empty space. All right, there was no path. So both of their models had electrons. Both of their models had the nucleus. But Rutherford said, oh, it's traveling in circles, Bohr's. And Rutherford said, no, negatively charged electrons just are in empty space around the nucleus. Now then we come to the modern atomic model. And in the modern atomic model, electrons form an electron cloud around the nucleus. All right? So here's your nucleus. And here is the cloud where all the electrons are likely to be found. They don't have no specific path, right? And that means there's no circular path, etc. They're just moving around in a cloud around the nucleus. Now, in this atom, electrons are more likely to be found closer to the nucleus than farther away. So you can see here it's represented, see how the electron cloud gets fainter as you go up? That's because most of the electrons will probably be closer to the nucleus. All right, and remember, the nucleus has the neutrons and the protons. So how has that model of the atom changed over time? Well, Dalton proposed, so here are these guys again, he proposed that all atoms are the fundamental particles of all matter. And he thought that all atoms were solid little balls. They couldn't be broken apart into smaller parts. They were just one big solid ball. J.J. Thompson did experiments and said, hey, well, wait a minute. There's an electron, or a negatively charged particle, inside that atom. Then Rutherford came along and he said, well, wait a minute. Something is making those rays bounce off. So there is a center of positive charge right in the middle. And he called this the nucleus. And then Bohr came along and he showed electrons traveling only in particular paths. Remember? He was all about the circular path of the electron. So that's how they changed over time. So now we have our modern, where we know it's the electron cloud. But then, all of a sudden, science continues to grow, and we discovered something called quarks. Because now they have powerful enough microscopes to look inside and say, well, wait a minute. Protons and neutrons are actually made of smaller particles called quarks. And they theorize that there are 6 types of quarks. There's up, down, charm, strange, top, and bottom. So these are the 6 types of quarks that they theorize are inside of protons and neutrons. Now remember, you're getting very, very, very small. And that's why they're theorizing, because, microscopes and our ability to see these things are becoming more and more powerful. So protons, they say, are made up of 2 up quarks and 1 down quark. So 2 up, 1 down. Neutrons are made of 2 down quarks and 1 up quark. Now the current atomic model might change. Like I said, once we get even more powerful microscopes, we might say, well, hold on a second. Quarks have something else inside them. And it just keeps going down and down and down. We don't know. So we're just theorizing at this point. So in summary, remember, if you were to divide an element into smaller and smaller and smaller pieces, the smallest piece would be the atom. And atoms are so small, they can only be seen by using very special, powerful microscopes. Scientists now know that the atom contains a dense positive nucleus surrounded by a negative electron cloud, or negative electrons in a cloud around the nucleus. So that is your lesson on what is an atom. We hope you enjoyed it, and we'll see you in the next lesson.